Hello and welcome to another episode of... Now, I'm not absolutely sure what to call this because we're in a transitionary phase. I'm going to call it the Fully Charged Show podcast, but it could also be the Everything Electric podcast. In fact, I believe that is what it's going to be fairly soon, but maybe not this time. I'm going to have a discussion with the board at Fully Charged Towers to make sure I've got that right. But anyway, welcome, because this is quite a long episode, but I think it's really worth you listening to because it is amazing. So a couple of quick facts that was intriguing. So we were talking about energy, the energy future, energy markets. Some of you may have seen the episode that was recently on the Fully Charged Show about my house and about all the technology that we have here. So we had a perfect example of that because while we were recording, we had, in fact, 4 short power cuts in our village. You know, and I've had to cut round it because I, for momentarily, lost the internet connection with my guest this week, as the hardwire that's going to the computer cut out, but the wireless cut back in. It's just it's complicated. But where I am sitting in my studio, where it's not protected by the battery system. The house is, but not this part. So all the lights went off in here, then they came back on, and then they went off, then they came back on, then they went off. And in that process, we carried on talking. You probably will notice that sign behind me goes out and then comes back. So that's running on just straight off the mains, nothing to do with the solar. No, it is running off the batteries. I don't even know how to explain it. It's one of the complexities of the wiring system in this house. Anyway, but what happened was there were some power cuts, which is very upsetting. But the house is absolutely nowhere. I know that my wife's in the house, and she didn't know we'd had 4 power cuts. She had no idea. Let's move on because one of the just before I introduce my guest, who is extraordinary. This is an amazing episode. One of the regular things that I talk about at this stage of the podcast is my energy. But just before you skip, I'm not going to plug anything because we are shortly going up to their factory. In fact, next week I think I'm going to see a new product, and I'm not going to talk about it now. I know what it is. It's very exciting. It is brilliant that they're doing it. I know loads of people are going to go crazy when they see what they're doing. Particularly now, I mean, the timing, it couldn't be more important to help people and to help more people to be able to have more control over the way they use the power that they need to live, you know, which is quite challenging here. I just want to quickly say that the price of natural gas in Canada has not gone up, not at all. And they've got loads of it and they don't care about anything. I think it's what they use for heating. It's one of the things I learned today. And yet we are, you know, so this is one of the reasons I think it's so important for Fully Charged to keep pushing a kind of more global view that often it's very easy to be blinkered down to like your street, your town, your house, like your boiler, all those things. And it's kind of important to occasionally think, wait a minute, how's everybody else doing it around the world? And that is where we're seeing this colossal transition. And I'm just going back to my energy. They are very much part of this. And that is they're having an increasingly critically important role in the energy transition. And that's really what the Fully Charged Show is about. It's about the transition and the difficulties. It's not straightforward or easy, as we discuss in this episode, but there are amazing opportunities and amazing benefits from struggling on. So I would like to welcome onto the podcast my guest this week, who's Paul Martin, and he runs a very small research and what do they call that? It's a research organization, but he helps different, particularly energy companies, chemical companies, to be more efficient, to be less carbon intensive, et cetera, et cetera. He is a chemical process development expert. Now, why would I have someone like that on the Fully Charged Show? I'll tell you why, because he knows what he's talking about. And I think this is really, really important that we find people that are really like involved in their particular worlds that can see the big picture as well and are able to communicate that to ordinary Joes like you and I. Joe is not gender specific. Just thought I'd mention that just to get that in first. And it is really interesting to talk to him. Now, one of the most recent episodes on the Fully Charged Show podcast / Everything Electric podcast was with David Seaborn, Professor David Seaborn at Cambridge University, about hydrogen. So we do talk about hydrogen quite a bit in this because there is this now growing network of scientists and engineers who are questioning the headlong, panicked, fossil fuel funded dash to use hydrogen for everything. And they're just sort of saying, no, hydrogen is critically important for some things, but not everything. And so we do cover that ground again, but in a very different way and with some fantastic insights. Paul is from Toronto in Ontario in Canada, which is the other side of Canada to where I was recently, where they have a staggering amount of renewables. So it's hydro. They've been hydro forever. So they have very sub 60 grams of CO2 per kilowatt hour, very low. We get to that occasionally in the UK with all the wind we've got, but they're like, that's their top level. It's usually below that. So that is very impressive. Our top level is 400-500 on a bad day. So, we need to do more about that. And we are, which is very hopeful. But so really interesting background of where he lives and what goes on there. And I really hope you enjoy this episode. It was an amazing experience to talk to him. I'm still high from it. So please, listeners, all the Joes, please do welcome Paul Martin from Toronto, Ontario, Canada, to the Fully Charged Plus / Fully Charged Show / Everything Electric podcast. Great. So just quickly, Paul, explain to me about Spitfire, because of course I thought of the aircraft, but actually I was wrong. So just fill me in on how that came about.
Sure. Well, Spitfire Research is the name of my little consulting company that consists just of me. The name comes actually from the project that kind of inspired my interest in electric vehicles, I guess, as an area of particular interest, and that is that this car bonnet that you can see hanging on the hanging from the wall there, from the ceiling, that's a 1975 Triumph Spitfire two-seater convertible that my son and I converted to fully electric in 2014. And I drove that back and forth to work for 4 years, spring through fall, as an electric car. And the project was done as a learning experience, but also because I was hearing all of this business about how efficient electric vehicles were, and I didn't quite believe it. And I wanted to make my own measurements to be sure. And so when I did the car conversion, it was easy enough to make the right measurements and to prove to myself that, in fact, they were as spectacularly efficient as they as was claimed, which is a bit of a surprise to me. But yeah, I certainly witnessed it. My car, that car, converting it from the original four-cylinder gasoline engine to an electric car operated from Ontario's excellent grid here with 40 grams of CO2 per kilowatt hour, actually dropped the emissions of that same car. So identical car, same everything about it. The only difference is the drivetrain was changed. It dropped the emissions by 97%, the CO2 emissions. And of course, the toxic emissions basically dropped to nothing. But the really amazing thing is that my other car is a Prius, which is the best car that you can buy that doesn't have a plug on it. It's still, you look at all of the specifications of all the cars, and if it doesn't have a plug on it, the Prius is still your best bet. And that electric car dropped my emissions relative to my Prius by 94%. Wow. So, almost two orders of magnitude. Amazing. It's just ridiculous. Electric vehicles here in Canada are a total no-brainer. But that inspired that project inspired the name. But unfortunately, in 2018, I was driving home from work and got hit by a big Dodge pickup truck. And the car was destroyed. But fortunately,
Right.
all the electric stuff came through the crash just fine. So I bought the car out of salvage out of the insurance deal, and it's now in a
Right.
1973 TR6. So that's my
Just,
that's my
I've
fun
just,
car now.
right. That's amazing. I've just got to quickly ask. I'm assuming you were okay in this accident. I mean, I'm afraid I'm worried about
Yes,
you more than the mechanics.
I was uninjured. I had a little bit of a bruise on my leg, but that was much less worrisome to me than seeing hundreds and hundreds of hours of my
Oh
time
God.
going,
Yeah.
ruined from a moment's inattention by a guy in a great
Yeah.
big truck that was, way too big to
Huge.
be on the road, honestly, and.
Yeah.
He just wasn't paying attention. A silent little car driving down the
Yeah.
road didn't notice it until he was shoving it sideways down the road in front of his bumper.
Right.
So fortunately, the car was low
Oh
enough that it
God.
wedged itself underneath his bumper, and that kept it from
Right.
flipping. Because if it had flipped, I'd be dead. So.
Yeah. Yeah.
I came through it
Wow.
okay. I
God.
mean, and the good news is that the electric stuff was all in another car now, and I'm not driving that on the highway, and
Wow.
I'm not driving to work anymore. I work for myself now through my little consulting company.
Right.
So, no commute is much better than a commute, even in a cool homemade electric car.
Yes, that's very true. But the interesting aspect of that story, though, is also which is critically part of it, is the grid where you live, because I mean
Yeah.
that is not the case everywhere. I mean, if you lived in Poland, for example, the CO2
Oh yeah,
content would
Poland
be
is a
higher.
very
I just
different
wanted to make
place.
that
That's
point,
right.
yeah.
But 80% of Canadians
what,
have access to a grid like mine, or better. 80% of us.
right,
And we're a G7
yeah,
nation.
that's pretty good.
So
Yeah,
it is pretty impressive. Now, there are a few provinces where the grid still, got a lot of coal on it. But Ontario burned
yeah.
its last coal in 2013. And Quebec and
Wow.
Manitoba and British Columbia are almost all hydro.
Yeah.
Our grid's got a lot of nuclear on it, but the nuclear plants have been very safe and they've worked very well. They're not cheap,
Yeah.
but they were built in the 70s, so we're still running them.
Yeah.
And,
Because I've just been
electric
in
vehicles
British
here.
Columbia, and I mean, I mean, I was very aware of how. Oh well, I don't know if you saw the episode, but we made an episode about the big hydro dam at Revelstoke in British Columbia, which is just short of 3 gigawatts. So it's very chunky piece of stuff,
I've
But
been
it's
to
amazing.
Revelstoke.
I mean,
I've never seen that dam,
oh,
but we have some huge projects in Canada, some huge hydro projects,
there was a bit of a freeze there.
we do have some huge hydro projects in Canada, and they are cold weather hydro projects, so they don't make a lot of methane emissions, which is good. In warm weather, hydro projects can generate quite a lot of methane, which is not, it's an undesirable outcome. They're not perfect, but they are way better than a lot of alternatives. And of course, the power is available whenever you want it. The amazing thing is Quebec has more hydro than anybody else going.
Right.
And
Quebec's, God, I didn't know that. Right.
Yeah, oh my goodness, Quebec has these giant projects, and Quebec has enough water behind their dams to run the Quebec grid for a year.
Wow. Sort of without further rain, sort of thing.
Well, I think rain and snow are taken into account, but the point being that the point being that the storage behind the dams is such a significant fraction. But yeah, as I was saying, the thing that seems to be happening in Canada at the moment is that there's I think it's quite understandable, but there's a lot of fantasy about hydrogen. And I have a long history working with making and using hydrogen, and am a co-founder of that Hydrogen Science Coalition. And you just had David Sibon on, my colleague, one of my co-founders, on the podcast recently. David and myself and 3 others founded that organization because we, quite frankly, were very fed up with the overselling of hydrogen as a decarbonization solution. And, it's something certainly that I don't believe in. I think that there's a lot that we can do with hydrogen, or that we must do with hydrogen, because hydrogen is actually a decarbonization problem that we haven't solved yet, and that we desperately need to solve. And we're not making progress on that. And yet people are selling the fantasy of wasting it as a fuel. And I find that
Yeah.
very unfortunate. I think it's contrary to the interests of decarbonization. So hence we founded that organization. And we hope
Yeah.
to provide information to people that is not based on a financial interest one way or another. It's not that I'm funded by
Right.
batteries or hydrogen or fuel cells or anything. My client base at my little consulting company is as broad as can be imagined. And
Right.
there's no obvious interest there one way or another. I just want people to make the right decisions about decarbonization because I have kids and I worry about their future. I see the
Yeah.
problem as being really important, and we have to be very serious about it and not fantasize.
Yeah. It is.
Yeah.
It is the most extraordinary argument because we've just had we have a party political conference happening in the UK right now of our current administration, who are, as you may or may not be aware, on the very extreme end of conservative politics. I mean, they're very, very hard right party. I was going to say company. They're kind of funded by some very big companies. It was potentially the wrong word. But it is one of the things that fascinates me is why the sort of more extreme conservative you go, the more likely you are to hear hydrogen is, the vital of future. And I can't correlate it because for me, hydrogen is a gas, doesn't have a political color to it. But I've just been trying to write something about this. That the kind of, well, on the flip side of that, I've never ever heard someone on the radical hardcore left who are opposed to private vehicle ownership and want us all to return to walking in public transport and bicycles, which I think is extraordinarily good idea, generally speaking, but probably hard to implement. But I've never heard them say hydrogen is the future. So why not? Why aren't they into hydrogen? Why is hydrogen ultra conservative? I don't.
Robert, you're going to bring out the rude person in me, and because I am someone who's known to a fault to call a spade, or in fact a shovel when I mean a shovel. I'm the kind of person that people are constantly telling, saying, well, why don't you tell us what you really think, hoping that I'll shut up. And of course I don't. But here's the reality of it. Let's imagine that you are a natural gas distributor, somebody that sells natural gas door to door. You can see that your days are numbered in a decarbonized future. You don't have anything to sell. And it's very important to you either to have a viable future, in which you're in business, still selling something door to door that people burn. Or if you can't imagine that, to at least give people the false notion that you have a future for a while, that the assets that, on your books are assets and make your shares look like they're worth something, are assets rather than what they really are in a decarbonized future, which is liabilities with an abandonment cost. And so these are the people that are behind the notion of hydrogen as a fuel. It's the fossil fuel industry. And then, of course, there are people that might be earnestly interested in decarbonization, but have just got the wrong end of the stick. So people, for instance, that are, either interested in directly in making hydrogen because they'll profit from it, like people that make electrolyzers and fuel cells and the like, or people that think they're going to be making giant quantities of renewable electricity and that we'll be making more of it than we'll know what to do with, which, I would say that's several decades premature. And I think some numbers here are instructive. Being an engineer, I'm very much a numbers guy, and it's really important to look at hydrogen as it is. As I mentioned, right now, hydrogen is a decarbonization problem, not a solution to much of anything. We make 120 million tons of the stuff a year, and substantially all of it, more than 99% of it, is made from fossils without carbon capture. That's the reality.
Yeah.
So in a decarbonized future, we'll probably need about 3/4 of that. We'll need about 90 million tons of hydrogen for sure, plus whatever additional we find uses for, like steel making or other things that we're currently doing using fossils and we might do with green hydrogen in the future. But taking that 90 million tons per year and working out, a very basic conversion from electricity to hydrogen, that would be 50 kilowatt hours per kilogram. And that would mean to decarbonize that 90 million tons of hydrogen that we'll need in the future for sure, would take 4,500 terawatt hours of electricity, which happens to be twice as much wind and solar as we made on Earth in 2019. Right. So, more than twice as much as all the wind and solar on Earth would be needed just to decarbonize the hydrogen that we will need post-decarbonization, plus whatever additional that we find uses for. And there are some good uses, like I said, steel making being one. And that's before we have any left over that we might consider using for poor uses like transport or heating. And let's be clear. I mean, I've literally got it down to a meme. One of these little 2-panel things. The one I used is the local hip hop artist Drake, who lives in Toronto here, of course, in a much nicer house than mine. I have 2 pictures of Drake, and one of them, Drake is going like this, avoiding something from a video of his, and it says hydrogen as a fuel. And in the next one, he's pointing with approval, and it says green hydrogen to replace black hydrogen. It's literally that simple. And of course, the Hydrogen Science Coalition has 5 principles that put a little more meat on the bones than the little meme. But the real thing is the whole hydrogen economy mythology is based around the use of hydrogen as a fuel. And it's kind of simple-minded thinking. Well, we burn stuff right now, and we can't burn it anymore because we're worried about CO2 emissions. So what else can we burn? Hydrogen. So hydrogen must be the solution. And it's a non sequitur. It doesn't follow. Hydrogen's a poor choice as a fuel. It's hard to move. It's hard to store. It's energy intensive to make. And when you burn it in air, if you burn it as opposed to using it in a fuel cell, you actually make nitrogen oxides, NOx, just like you do when you burn anything in air. And in fact, you make more because the adiabatic flame temperature is higher, and that means you make more. So, when you dig into it, when you look at the whole hydrogen as a fuel thing, the devil's in the details, and he's not hiding. He's waving his pitchfork at you with one hand, and in fact, the other hand is extended with the middle finger raised. There he is. He's waving at you. And, I used to be a big fan of this notion back when I was in university, as an example. I thought back when I was driving that Spitfire as a gasoline car, I thought hydrogen certainly looked like the thing to do, because if nothing else, we could capture the CO2 and bury it. And that would give us a hope to use the energy in fossils for a bit longer. And the more I learned about it from doing actual projects, numerous projects, trying to turn hydrogen into something that made sense, the more I realized that it was just, it was a square wheel. You couldn't fix it without making it into something else. So, it's unfortunate.
A thing that I learned that I genuinely never thought about, and I just want to make it really clear that I didn't pose a leading question that led to this piece of information. This came out of the blue. I was interviewing fire officers regarding, I was interviewing like a number of people at a conference about electric vehicle safety. There were 2 amazing fire officers there. And there was a whole discussion about how hard it is if batteries catch fire. It is harder to put that out than if gasoline catches fire. There's no argument about that. But they don't catch fire very often. But there was that side. And then one of them mentioned hydrogen. And I said, well, I suppose that can be quite risky. And he said, well, I don't think we'll ever know, because they had done tests. So the British Fire Service had done tests where they put hydrogen fuel cell cars, not anything else. And he wouldn't say which cars because he didn't want to be rude about any manufacturer. They put them in They put them in effectively like a warehouse, like a garage, like a big building, kind of but close the doors, like a sealed building, like I don't know what you call it, a barn, a big barn thing, but with a roof.
Sure.
And had monitors up in the roof, and a substantial quantity of hydrogen was released by those vehicles over a 24-hour period, which made them, as fire officers, terrified of the prospect of, Old Dave gets there in the morning with a cigarette hanging out of his mouth, opens the door. That's when and they said, all their research has shown that how leaky hydrogen is, even when in a properly manufactured car where they've really gone to the nth degree to stop it leaking, it still does. And I don't think they weren't claiming anything dramatic like, if you've got a hydrogen fuel cell car in your own garage, it's going to blow up. No, they're not saying that, because it's fractionally small amounts. But if you've got, say, 20 large commercial vehicles with huge high pressure tanks in a storage facility, which is a sort of place those, or a distribution center or something, they're indoors. They think that's a danger that has been sort of verified, which is, you can go, oh God, that's not good. But I think, that side of it, when people talk about the Hindenburg, is a kind of false flag sort of.
I agree with that. I mean, we handle that 120 million tons of hydrogen in an industrial context almost without incident. I mean, we've really learned over the past 100 years or so how to handle it. But of course, Robert, we make a lot of compromises in doing that. So one thing that we don't do in the chemical process industry is store it at 700 bar. At 10,000 psi, which is the pressure that it's stored on board a hydrogen vehicle. We don't do that. Yeah. Why do we not do that? Yeah. Because it's mad. Because it's mad. It's the result of contending rather desperately with the properties of hydrogen. And of course, a lot of people who don't understand the physics very well just, they hand wave it and they say, oh, don't worry, we'll invent a way out of it. No, in fact, we won't. The things that are broken about hydrogen as an energy storage medium or as a fuel, they're fundamentally broken. They're not things that are amenable to being repaired by either innovation or wishful thinking. You can't just hand wave them away. The inefficiency problem that hydrogen has, the reason that, when I did the calculations and I compared the Tesla Model 3 versus the Toyota Mirai fuel cell vehicle.
The Mirai, yeah.
It takes over 3 times as much energy from source to move the car the same distance, and which means inherently you're going to be paying 3 times as much for just the energy. And then you have all of the distribution and other equipment that you have to pay for. Somebody needs to earn a return on that. So that means that, in fact, that the cost of the distributed fuel ends up being 5 times as much. Over 5 times as much per mile driven as for the Model 3, which uses electricity directly. And, this inefficiency, people say, oh, well, it's inefficient because we haven't been doing it and we'll find ways to do it better. And that's not correct, in fact. The inefficiency arises from 2 things. The very first thing is too many steps. So each step, making water, using electricity to split water apart into hydrogen and oxygen, that step has a maximum efficiency associated with it. And then storing the hydrogen at high pressure has a maximum efficiency associated with it. And then making that hydrogen chemical energy back into mechanical energy, or electricity in order to move a vehicle, that has its own inherent inefficiency associated with it. And the product of those 3 efficiencies is just too low because there are 3 steps. And the other problem that hydrogen fundamentally has is the properties of the molecule. And you can't fix those. It is inherently big. It occupies a lot of space. And even squishing it down to 700 bar, 10,000 psi, which is, as I mentioned, mad from a chemical risk perspective, given how slippery this stuff is, how diffusive it is, how it likes to make its way even between the grains of metals in an attempt to escape its bonds. It's a reaction to its poor properties. And even as a liquid, it's only 71 kilograms a cubic meter, which is not very dense, per unit mass.
Because what would gasoline be?
Well, gasoline's more like 850 kilograms a cubic meter, so it's more than 10 times as dense. And then And then, of course, it's a liquid that you can pour from place to place.
Yes.
Hydrogen
Yes.
has a whole bunch of unfortunate properties. One of them is when it expands, when you expand the gas, it heats up. So one of the things that people don't
Right.
realize about hydrogen refueling stations is that they need giant chillers to be sitting there to pre-chill the hydrogen
Yeah.
so that when it expands from the storage tank into the tank on the Mirai or whatever car, it doesn't overheat the tank. It doesn't cook the tank as a
Right.
result of this weird property of hydrogen above quite cold temperatures, like around room temperature. It heats up quite a lot when it
Yeah.
expands. And if you just let
Right.
it expand into a tank, it'll overheat it. And the bigger
Right.
the vehicle, the worse this problem gets. So it's worse for trucks than it is for cars.
Right.
And
Right.
the people that are in the know about hydrogen, people like me, understand these things. But there are a lot of people who seem to be, you'll see my Magritte painting over here. They seem
Yeah.
to be smoking the pipe that's full of hopium.
Yeah.
They are just wishing. They're using the power of wishful thinking to just
Yeah.
wash away these unfortunate properties of
Yeah.
hydrogen, or hope that someone like me will come along and invent us a way to make it into something worthwhile. And I'm sorry, it's
Yeah.
a square wheel. The only way you can make it into
Yeah.
something better is to turn it into something it's not.
Yeah.
So
Because I mean that what the
hydrogen is a
one
fuel.
area. Yeah, yes. I mean, I'm with you. But I mean, the one area that I guess the only hopium I've smoked is from the point of view of sort of longer term storage. So I went to see was it called a compressed air energy storage system at Birmingham University.
Sure.
It's quite a big industrial scale thing. So I don't know what pressure they pressurize it to, but I can understand that you have a pump that compresses air in a massive tank, and then that uses energy, and then when you want to release that energy, you take that highly pressurized air, run it over a turbine, and produce power. And I'm sure I don't know what the losses were; they would have been, but you can understand that. So I was hoping, because I've also seen systems where there's an electrolyzer, some tanks, and a fuel cell, which can then be a remote power source. Or you can store energy in the
Sure.
terms of hydrogen. So there was no burning taking place. It was all.
Yeah.
But the more I hear about the problems, the inherent problems of hydrogen, you just go, because that struck me as if we could have somewhere, a terawatt hour of compressed hydrogen energy storage in a big industrial thing. That would be brilliant, because there's no
Sure.
CO2 involved.
It's a
You're
very
not burning it.
popular.
Yeah.
It's a very popular concept, and I think it's kind of a myth. So let me explain to you
Right.
what I mean by that. The storage part is actually not that hard. Now, it's
Right.
geographically or geologically kind of specific. You really need a salt cavern. So you need to find
Right.
a giant quantity of salt that's buried at a suitable depth in the earth. And then you have to mine the salt out of the ground, out of the earth,
Yeah.
with water, and dump hopefully with seawater. And then you dump the salt into the ocean or dilute enough way that it doesn't kill the sea life that's nearby. And you end up with
Right.
a big hole in the ground that's basically a hole in a giant chunk of salt. And then you can shove hydrogen into that, and it'll stay there more or less, and it'll stay pure more or less if you make a new one,
Right.
right?
Yeah.
So the storage part looks okay. It looks like you could do it, and you could do it at fairly large scale, assuming that you have these salt caverns that you could use. If you have to use above ground tanks or things like that, you're in trouble already. The cost of
Oh, right.
storage is actually a lot higher than people think.
Right.
But if you could do this giant salt cavern thing, that would be okay. But here's the trouble with the whole notion of seasonal storage, because that's the thing that everybody's on about. They're thinking about,
Yeah.
how do we take excess wind and solar in the summertime when we don't have heating demand, as an example. We're not trying to keep ourselves warm with that electricity.
Yeah.
And the sun shining most intensely. How do we take that excess renewable electricity from the summer and put it away so that we can use it again as electricity in the winter? And the challenge there is that although the storage part of it you could do, there are two things that kill it. One of them is the cycle efficiency. As I mentioned, the efficiency in terms of lower heating value, which is the relevant figure here, the efficiency of making electricity into hydrogen lower heating value is about 70% best case. That's about 83% on a higher heating value basis, without boring people with the
Right.
detail. But the point is that it's pretty close to as good as it's going to get. It's never going to get to 100%. 100% on a lower heating value basis is just not going to happen. So 70% is about as good as you can get in electrolyzers that you can afford at the moment. And then the storage part of it might be about 90% efficient. And then the fuel cell, if you buy one that's really quite a bit larger than you need so that you can use it at a fraction of its output, so it's very efficient, that might be 60% efficient. So when you multiply those out, 0.7 times 0.9 times 0.6, you get 37%, which is a really terrible battery. That would be bad enough. Buy 3 kilowatt hours, feed them into a machine, get one back out again. Not very good, right? Even if the storage part of it is cheap. The other problem is that these equipment, they're expensive. They're not just not cheap, they're very expensive. And so the notion that you can make a cheap commodity like energy or hydrogen as a storage medium for energy using expensive equipment that you don't use very often it does not make sense, right? So that's the trouble. This capital cost that you have to put in fact, even if you only use it, you buy a megawatt worth of electrolyzer as an example, and you feed it at 30% capacity factor from an onshore wind project. You only make 30% of the hydrogen that electrolyzer could make, and the other 70% of its capacity is wasted. You've paid for it, but you're not using it.
Yeah.
And by virtue of just simply putting that electrolyzer in a different place in the world, where there's a combination of wind and sun that gives you a capacity factor instead of 30%, it gives you a capacity factor of 70%. Now, these are very specific places, deserts with an ocean to the west, places like Western Australia, Chile, maybe parts of the west coast of Africa. You buy the same 1 megawatt worth of electrolyzer and you put it in this different place, and now it makes more than twice as much hydrogen per year as it did elsewhere. So the logical thing, if you want to make cheap hydrogen, what you do is you buy your expensive electrolyzer and you put it somewhere where the energy is available at low cost with high capacity factor. And the trouble there, of course, is that you're left with the problem of, okay, great, now I've made hydrogen out of this electricity. What do I do with it? And as it turns out, moving hydrogen around is quite a bear. It's very difficult. It's something that we don't do much of. I think last figures I saw were that about 8% of the hydrogen that we make in the world, of this 120 million tons that we make and use, only about 8% of it moves any distance at all. The other 92% is used right where it's made, like right across it goes from the hydrogen steam methane reformer plant right next door to the hydrotreater or the ammonia plant or whoever's using it. So the thing that makes sense to me as a chemical engineer, who's again worked on hydrogen for decades, is that what we'll do is we will do all of that good stuff, that replacing of black hydrogen that's right now made from fossil fuels without carbon capture. We'll replace that black hydrogen with green hydrogen that's made in those good places, the places where we can make it cheaply. And we will do that in order to make products like ammonia that will be low in carbon intensity. And we'll use the ammonia not foolishly as a fuel, but instead we'll use it as a fertilizer, which is how we use substantially all the ammonia in the world right now. We use it either as a fertilizer or to make other fertilizers, to make nitrate and urea and stuff like that. And so what we'll do, hopefully, if we're smart, in a decarbonized future, is we'll make ammonia for use as fertilizer in places in the world where we can make it most cheaply, because they have awesome wind and solar hybrid resources. And we won't waste it as a fuel. This notion that we're going to turn hydrogen or ammonia, liquid hydrogen, whatever, into the new LNG, the energy export chemical that we ship around the world to places like Japan or South Korea that have large populations that are very energy hungry and right now are very dependent on fossil fuels. I mean, forget it. The notion there is that by the time you've involved something like ammonia, you've got all that many more steps. Another chemical step to make the chemical hydrogen into the chemical ammonia, and then you've got to ship it.
Right.
And now you've got to break the ammonia back apart again to make hydrogen, or you've got to burn it. When you include all those steps, the cycle efficiency drops from that 37% for pure hydrogen that I mentioned down to between 11 and 19%. So now it's buy 10 kilowatt hours, get one or two back.
Get one. Yeah.
Wonderful business if you're selling kilowatt hours. Terrible business if you're a consumer of energy. And, so honestly, I think Japan and South Korea, as examples, are in deep trouble in a decarbonized future because I don't see, they're not comfortable with buying renewable electricity from their nearest land neighbors by virtue of cables. That doesn't look like an appealing proposition because they don't like their nearest land neighbors that much. And the worry is that every time that they say something wrong and annoy their neighbors, the neighbors are going to put their foot on the cable and kind of step on it a bit and give them a little less energy so that they smarten up. And they want to import something by ship. They want that desperately.
Yeah.
The trouble is hydrogen ain't it. Hydrogen's a poor fit for that. It's by poor fit, I mean, it will be so costly that anyone that predicates their economy on that basis is going to go bankrupt. I mean, the people that don't have to do that because they can use electricity directly are just going to outcompete them totally on the basis that, on any industry that involves significant amounts of energy. So, the notion of hydrogen as an energy export medium is one of the things that the Hydrogen Science Coalition really thinks is not a thing, not going to be a thing, and not something that we should count on. We talk about it more from the point of view, if you need hydrogen locally, you should be making it locally. Don't think about importing it from grand distances. But of course, if you need a molecule made from hydrogen, or steel, as an example, made using hydrogen so that we don't emit a bunch of CO2 in making steel, then we should make those things in the places where renewable energy is abundant. And available with good capacity factor, because that'll make it cheap, and cheap's good. Cheap is good from the point of view of making the transition less impactful on people's lives. It's going to be disruptive enough to get rid of these fossils. The other thing that I don't think people realize, and to me as a chemical engineer, it really strikes me as an important point that a lot of people miss, and that is. When you look at petroleum as an example, you look at oil, that's the source of about 10,000 different molecules and materials that are really important to us. I mean, super important to a modern life, important to health, important to safety, important to, the functioning of an economy and so on. And what do we do with 75 to 85% of the barrel of petroleum right now? We make it into stuff that we burn. And Dmitry Mendeleev, the father of the periodic table, a guy that came up with the periodic table of the elements, somebody asked him, "What do you think about burning petroleum?" And he said, "Well, I suppose you could, burn banknotes in your kitchen stove too to keep warm. But I don't think it's a good idea." And because that was his point. It's like, come on, man, this is the basis of all of the chemical industry. It's the basis of all the molecules that we make. Why are we squandering it as a fuel? It doesn't make sense. Right. And that's always puzzled me, because I've spent decades trying to help people, as an example, make important molecules that we want to use in the future, starting with biomass. Starting with wood or corn stover or agricultural residues or biogas or something else. And it's desperately difficult. It's difficult and it's expensive. And there's no need to do it if we just stop burning this stuff and we use it instead. We won't have to make any new inventions in order to find a way to do that. We know exactly how to do that right now. And why are we not doing it? Honestly, it's because we don't want to, because we think it'll be expensive or it'll be difficult. Yeah. Very frustrating.
But that's a critically important thing. I mean, I had the privilege many years ago, before the Fully Charged show, to spend 2 days filming in a really big oil refinery in the UK.
Hmm.
So, and that was the two things that stayed with me from it. Are one, that it used huge amounts of electricity, which I had no idea that
Hmm.
an oil refinery uses a lot of electricity. But two, just the quantity of products that oil refinery produce. So they do a huge. I mean, they do about a third of all the fossil fuels we burn in transport in the UK.
Right.
It's a very big refinery. So the
In
shipping,
one
so the
place.
bunker fuel, the jet fuel, diesel, petrol, and hydrogen and all those things. But also, because I didn't know that. I mean, if I knew it, I hadn't really grokked it. But the pharmaceuticals, the fertilizers, the plastics, all the other stuff, and I do remember thinking even then, should we be burning this stuff at
Yes.
the rate we are? But then what I think I've had, so you'll know this, but I think I've had that explained to me is that if you take a barrel of oil,
Hmm.
I was told, and I hope I'm wrong, and I'm sure I am, you couldn't turn all of that into, say, pharmaceutical chemicals or fertilizer or plastics. Some of it when you refine it, some of it's just going to be fuel. I mean, is that not the case? Is that too simplistic?
I would say that that's quite conventional thinking, and I would say that it's also
Right,
not necessarily the case. I think there are that
right,
it's very easy to optimize a refinery around making fuels if that's the thing that makes you the most money. And that
right,
if you have byproducts, as an example, from making a particular molecule that you want, and those byproducts are a mixture of different chemicals, and there's not very much of them, you don't want to spend a whole bunch of money on equipment to separate them one from the next. What you do is you bung them into a burner somewhere where you need to make heat, like, and in a refinery. That's actually where about 20% of the energy in every barrel of petroleum ends up. It ends up as fuel gas that gets burned
wow,
in the refinery. And so
yeah,
that makes petroleum refining about 80% efficient, round numbers. So
right,
81 to 83% efficient in terms of, the
right,
number of units of heat energy in the barrel of petroleum versus the number of units of heat energy in all the products made by the refinery. And so gasoline and diesel are about 81 to 83% efficient. But I
right,
remember, in fact, this was the very first article, Robert. I do most of my publishing on LinkedIn because I love the way that LinkedIn allows me to do two things. One of them is it allows me to edit my articles when I learn new things and when things change, so that they're not
yes,
a stick driven in the sand 10 years ago that people keep
yeah,
referring to, and I have to go, no, that's changed, it's wrong. I'm sorry, it's still there, but it's wrong. I can
yeah,
fix it and make it right. And the other is that I've got this wonderful following of thousands of people that in some cases have forgotten more about little arcane points of technology than I'll ever know.
right,
And they will say, oh, no, you're not quite right on that, Paul. You really should think about it
right,
differently. And here's the reference. And they'll correct me, and they'll move my knowledge along. And so, anyway, the very first article I wrote about energy related matters on LinkedIn was in relation to this claim, and it was actually made in the sequel to the Who Killed the Electric Car? What was it called? The
right.
Revenge of the Electric Car, or
The
something?
Revenge of the
And
Electric Car. Yeah.
yes, that's right. And during that sequel, Elon Musk was interviewed, and whoever he was speaking with prompted him and said, well, there a lot of electricity is used in refining petroleum, and I bet you we could probably run your cars, run electric cars about as far on the energy not used in making a gallon of gasoline as they would run on that gallon of gasoline. And go, oh yeah,
Yeah.
yeah, yeah, that's probably right. And it's completely wrong. It's totally wrong, because it commits what I've been referring to affectionately as the second sin of thermodynamics. So that the first sin of thermodynamics is the worst one, and the first sin of thermodynamics is assuming that some process makes more energy than you've put in.
Right. Yes. Yeah.
The law of conservation of energy is pretty solid, the first law, and so if you sin
Yeah.
against the first law and you claim that you've got some process that can run itself and make excess energy, and you've created a perpetual motion machine, and it's wrong.
Yeah.
So that's the first sin. So of course we don't like the people who commit the first sin. But the second sin is
Yeah.
a little bit subtler, and that is, and I think David Saban was talking a bit about this too. This is a really important point, and really irksome to an engineer, and that is that energy is rather like currency. So if I said to you, "Here's $100," you would probably say, "Thank you."
Right.
Yeah, you would say that's
Yes.
great. But if I didn't mention to you that I was giving you 100 Jamaican dollars, you'd probably be a little bit
Right.
disappointed because you probably thought I was giving you 100 US dollars. And energy is exactly like that. It's denominated in units like joules or British thermal units or kilowatt hours or the like. And those are all units of energy, but there's an exchange rate among them. Okay, so there's really
Right.
only two kinds of energy that we have to concern ourselves with thermodynamically. One is heat, or proxies for heat, like chemical energy, and the other is work, which is like mechanical energy, or electricity, which, electricity is like the universal currency. You can convert it with high efficiency into any other form of energy that you want. So it's kind of perfect stuff. And when you look at that refinery problem that I just mentioned, 80% of the energy in the barrel ends up in products, and 20% gets wasted in the refining process. Of
Yeah.
that 20%, only about 15% of the 20 is used as electricity. The other 85% of the 20 is used as fuel gas. So it's chemical energy,
Right.
it's heat. And so, what these guys had been doing in this conversation about electric cars is they had basically converted the 20% of the energy that's used in refining petroleum into electricity with 100% efficiency, which you can't do.
Right. Yeah.
Right? It's like saying, well, I've got $100, and that means I've got forget that they're Jamaican dollars. Let's assume it's 100 American dollars. Oh, look at all the stuff I can buy, and energetically, they've committed the second sin. But, Elon's a smart guy, and he just got tripped up in that conversation, I would say, not thinking about it very carefully in the heat of the moment. But there's this professor in Canada named Václav Smil, and he is a terrible sinner of the second kind, is this committer of the second sin of thermodynamics, because what he's always on about is primary energy. We make so much of our primary energy from fossils. Oh, the transition away from fossils is going to be impossible.
Right.
And there's the thing. This primary energy business, basically what we're doing is we're saying, okay, I pour a gallon of gasoline into my car and I burn it, and I get 15% of that energy out as mechanical energy to move my car forward, and 85% is wasted as heat. But I'm going to imagine that in the future, I need to make all 1 gallon's worth, all 39 kilowatt hours worth of energy that's in that gallon in order to drive my car in the future. And of course, we don't have to do that because we've got these electric things that are, 5 times as efficient.
Yeah.
And use the energy that we're going to be making in the future, electricity. They use it directly with high efficiency. Yeah. And that's the thing that, now, okay, the transition away from fossils is still going to be hard, but it's going to be about a third as hard as Václav Smil imagines it to be.
Right.
If we're not sinners against thermodynamics, the transition's easier than we think. So, and I see that as a hopeful sign. It's something very important.
But I mean, I think certainly the comment. I'm just going on the kind of comments that we get on our shows and on Twitter and all that sort of stuff. Is the anxiety, particularly in this country? I think it's fairly specific to us. I mean, this is one of the joys of making this show and getting information from around the world. So talking to you in Canada, and I talk to people in Australia and China and everywhere, Africa even.
It's remarkable, isn't it?
That it's a very different, but also that story is very different. I mean, I like to compare the UK with Poland. I mean, we're very blessed by having an enormous amount of coastline and very shallow water around us, which means we can put in staggering amounts of offshore wind, which we're in the process of doing. And it really is. We were 62% of all our electricity during the day, working day in this country was wind yesterday. I mean, it was a windy day, but the fact that
The
it's 62%,
transition of the UK
extraordinary.
grid, the transition of the UK grid has just been, it's made me smile from ear to ear. It's so lovely to see. Now, of course, we in Canada, we had the good fortune that we had this giant landmass and such a large fraction of the world's fresh water and resources, per capita, just unbelievable. So we're very fortunate. And as a consequence, we have a much easier time, I guess. Our grids are already largely decarbonized. It's really Alberta and Saskatchewan and a few of the eastern provinces that we need to work on. But watching the UK, it's just been, oh my goodness, it's so heartening as an indication of the fact that we can, in fact, imagine this transition happening. And in fact, I'm super hopeful about this. I'm not hopeful about hydrogen as a fuel, but I'm very hopeful about our ability to decarbonize the economy. I see it as not only possible, I see it as practical. And the other thing is that eventually it's inevitable because these resources are not, fossil resources are not renewable on the human timescale.
Yeah.
They might be renewable on the geological timescale, but we're using 10 million years worth of fossils every decade. So that's not renewable. That's not a pace that's renewable.
That's difficult.
So we have, exactly. Eventually nature's going to wean us off them. And it would be really great if we could instead use them for those high value uses to humankind to make, materials and chemicals and so on, and stop wasting them as fuels as soon as possible. And, the big problem that we have in that regard is that we have to get the policy in place to make that an economic proposition.
Yeah.
For decades, I in the former company I used to work for, and now to some degree, to a lesser degree in my private consulting business, I found it very frustrating for people. People would walk in, bright, motivated, creative people would walk in and they'd say, hey, we've got this great idea. We can decarbonize whatever it is, something or another, some chemical, some material. And all we need is about $50 a ton CO2 tax in order to make this thing make economic sense. And of course, we would build them we'd design and build them a pilot plant, and reality being what it is, they'd find out that no, in fact, they were a little optimistic. It would actually they'd need $100 a ton in order to, break even and start competing. And of course, they would bet that we as a society would put in place that $100 a ton carbon tax, and then we wouldn't, and they would go bankrupt. And it's very depressing because we seem to want something for nothing, and I can only think of one something for nothing situation. I can think maybe of a few more, but there's one big one from my career. It's one I'm fairly proud of. Two smart guys from California walked into our facility back in 2013, and they basically what they said was, we've been thinking earnestly about the difference in price between petroleum and natural gas. And we think natural gas is going to be structurally cheaper than petroleum for a long time, for good reasons that we think are defensible. Right. And so we see an opportunity to make something from natural gas that we currently make from petroleum as a way to make money. But we also want whatever we do to be robust against climate change. So if carbon taxes come in the United States in the future, we want that to make us more money, not less. But we know it's not going to happen in the short term. So whatever we do has to make money the way it is. And they had done a very exhaustive evaluation of all the different things that we make from petroleum that we could instead make from natural gas. And they rejected all of them. And there were all kinds of people betting billions of dollars on making this or that, because this was not a new idea, it was clear that the price of natural gas was going to be structurally low for a long time, and lots of people had noticed. But they were all betting on the wrong things. And these guys had said, those guys, they're all dumb. They're all betting on the wrong things. They settled on the least sexy thing you can imagine: carbon black. Now, what is carbon black? Carbon black is this greasy black crap that is used as a reinforcing material in rubber. It's the thing that makes tires black, and any number of rubber goods black. So it's not just the fact that it's made out of carbon and that it's colored black. it has a certain shape as a molecule. It's got kind of tendrils like this flying spaghetti monster. And that helps it interlace with the molecules of the rubber and provide reinforcement. It provides beneficial properties. And so how is this material made today? It's made by partially burning the dirtiest garbage off the bottom of the crude distillation column, or the vacuum distillation column, the residuum. You partially burn that, and you get this horrible emissive process ends up making carbon black, and that's how it's made. And in fact, it's so filthy that carbon black plants are used as landmarks by pilots. Look for the plant that's got the black splotch around it a mile in diameter, and you'll know that you're in such and such a town. So anyway, these guys had decided that, well, hey, we can make carbon black from natural gas, and we can do it in a way that doesn't result in any CO2 emissions. And in fact, the byproduct of this process is hydrogen, which they use to make ammonia. So these guys came to us, and we designed and built them a pilot plant in 2014, and they worked on it for many years, spent many millions of dollars, and got the process to work. It makes carbon black really well. It makes hydrogen, which they make into ammonia. They plunked their plant down in Nebraska, which within a 100-mile radius of their plant are 40% of the ammonia users in the United States. And the carbon black they can ship anywhere. And they're getting their electricity from a nuclear power plant that was built in anticipation of demand that never materialized because nobody wanted to live in Nebraska. And as understandable, I guess, although it's a pretty enough place if you look at it closely. But anyway, the company's called Monolith Materials, and their process is really quite amazing. The U.S. Department of Energy actually gave them a loan guarantee to the tune of $1 billion to take their first commercial plant and scale it up by a factor of 10 so that they're a real producer. And of course, I see this as being really exciting and interesting, but I'm also realistic about it, because when you look at how much hydrogen we need, remember we need 90 million tons. If we were to try to make 90 million tons of hydrogen a year using this process that these guys had come up with, we would make 270 million tons, barest minimum, of carbon stuff.
Right.
And the whole world market for carbon black and graphite, and all the batteries that we need that will have graphite in them and so on, is 1/10 of that. It's less than 1/10 of that. So imagine, 90% of the material ends up going into reverse coal mines, and you have to pay to dispose of it. The economics of that don't look very exciting. But while you're replacing a product that's made by a dirty emissive process from petroleum, it looks very good. Looks wonderful, actually. And kudos to them. Like I said, very smart guys that walked in, and they had not accepted the conventional wisdom, and they weren't pie in the sky about it either. They were very realistic and said, it's the United States. We're not going to have carbon taxes, not for a long time. So we can't count on that. We need something that'll make money without carbon taxes, and yet decarbonize something important. They managed to decarbonize both of those things, carbon black and ammonia production, and to do it in a way that makes money without carbon taxes. But that's rare. That's one project out of hundreds of projects over decades. So we can't count on those purple squirrel type projects to rescue us. Every little bit helps. But as the late David Mackay said, every little bit helps, but it only helps a little. We need to go after the big bits. And cars, they're a big bit. Heat pumps for heating homes, they're the big bits. And what drives me crazy about the hydrogen thing, Robert, is people are always on about, it's perfect for the hard to decarbonize sectors. And then there's always what do you mean by hard to decarbonize sector? And so why, of course, the thing I want to use hydrogen for, whatever that happens to be. Now, it turns out that most of them are not actually all that hard to decarbonize. But it does beg the question as well. Why in the heck would we focus on the hard to decarbonize sectors? Why wouldn't we be working on the easy ones? The ones that are easy to decarbonize, that we can decarbonize cheaply. In fact, with the electric car, as an example, we can make the total cost of ownership of the car less such that the cost per ton of CO2 emissions averted is negative for the person that owns the car. I mean, this little car here, as I mentioned, the car itself was wrecked, but the battery system and the inverter and the motor and all that stuff all came through the crash just fine.
Survived.
No fire, lithium iron phosphate, nice and safe. And it's all in another car driving around again. And it paid back its embodied emissions, the energy that it took and the emissions that it took to make the battery. It paid that back in less than a year. And I drove the car back and forth to work for 4 years before the crash, and I'm still driving it around, almost 10 years later on that same battery pack. So, electric cars, like I said, they're a no-brainer. They're the easy to decarbonize sector. That's what we should be going after hard. Heat pumps, same deal. Yeah. A little bit harder to justify because natural gas, for instance, here in Canada, natural gas is still super cheap. It's just so cheap that replacing it with electricity is difficult to make economically viable. It would take quite a lot of carbon tax in order to make that work out. And even in Canada, although we have a good carbon tax that's well supported by the public, that carbon tax won't be high enough to make a transition away from natural gas to heat pumps for home heating look attractive, in the next decade or so. Certainly not something I'm going to jump on doing. Last year, in the height of the pandemic, my gas boiler kicked the bucket, and I replaced it with another gas boiler. Partially because I needed to do it in a hurry because it was February and it gets desperately cold here in February. So I had to do something fast, and the heat pump wasn't going to be fast enough. But when my air conditioner finally dies, I will definitely be replacing it with a bidirectional heat pump. Because that just makes good sense. It's the same machine. It just has a few other, bits and bobs on it in order to make it bidirectional. And that'll be a no-brainer. Had I been smarter, I would have done that up front. But I guess I just wasn't planning for the future well enough. I'd done the math and realized that, gas is just so cheap. I'm going to heat with gas. There's no question about it. Why bother with the extra cost of the heat pump at this point? Yeah. So short-sighted
that's very much... No, well, yes, sort of, but also very understandable. I mean, that's one of the big shifts we're seeing here, because we used to have cheap natural gas. Now we have the most mind-bogglingly expensive natural gas, is off the scale. So, and there's a lot of interest in heat pumps and batteries now in this country. My goodness.
The cost of that's the other thing that a lot of people don't seem to realize, and I get it to a high level because my wife and I have a little farm about an hour and a half's drive east of Toronto, and it's back in the woods. Although we could run a bunch of power poles and get an electrical connection to the grid and pay a monthly fee to maintain that, plus all the cost of all those wires and poles, that's just, the cost per kilowatt hour that we use up there would be mad. So we have solar and batteries. And, solar and batteries do a wonderful job. And when you have a system like that, an off-grid system, you learn a few things that other people, sophisticated people that, design electrical systems don't seem to understand at the level that I do. And that is, for instance, panels are cheap. So how many panels do we have? We have the number of panels that we need to meet our winter demand. Do we cry any tears about the electricity that we make in summer in excess of our needs? No. The panels don't make it. They just you turn them off and they just sit there and they do nothing. Now we actually use it to run a little freezer, so we can have cold drinks up there and so on. And of course, we don't run that in the winter because it's cold outside. We just move the freezer outdoors and get all the cold we want. And how much battery do we have? We have as much battery as we can afford. But the batteries that we have, a good friend of mine and I went together and made an Alibaba purchase of some lithium iron phosphate batteries. And when we bought them, they cost us under $100 per kilowatt hour, including shipping to Canada. Retail Now, we didn't buy a
Right.
container load of them, Robert. We bought,
No.
I bought 8 kilowatt hours worth, and he bought 16.
Right.
And we had them shipped, and he's got a nice off-grid system, kind of whole home UPS arrangement with solar panels on his roof and 2 inverters, hybrid inverters, and a nice big battery pack, which he's just recently doubled in size because he's so pleased with it. And I just have the little system up at the farm. But when you run the numbers on that, those batteries are good for at least 3,000 cycles. At least. Building a pack out of them cost $20, because that's how much the AliExpress.com BMS cost.
Right.
And they come with the bus bars and so on. You just bolt them together. Their prismatic cells is super simple. Anybody can do it.
Yeah.
Like I said, the BMS was $20, and good for 3,000 cycles. And if you do the math on it, every kilowatt hour that you get back out of those batteries costs you about 5 US cents per kilowatt hour over their lifetime, which is pretty cheap. Which is actually to the point where I could do day-night arbitrage, because we have time of day pricing here in Ontario.
Right. Oh, you do. Right.
I could do day-night arbitrage, charging up my battery bank in the evening, and then discharging it to cover my loads during the peak periods, and I could make money.
Yeah.
I could make money. I don't need any solar in order to make money. And people, for some reason or another, they think, oh, well, this, making the grid renewable is impossible. Oh, it's too hard. It's too hard to imagine. It's not, my goodness, I can imagine it. And I'm not honestly all that imaginative a guy. I'm a pretty skeptical guy and a pretty penny conscious guy. And I can see it. So, and then they always ask, well, what do you do for the last little bit? What happens when you've had a big snowstorm and the panels are covered in snow and there's no wind blowing? We don't have a wind turbine anyway. It doesn't matter to us. But what do you do when the panels are covered in snow and you still need a little bit of power? So, well, I've got a gasoline generator. Now, I run it more often just to make sure that it will run when I need it than I actually run it to make power. But I have it there. And the great thing about it is that although it's not very energy efficient and it might make some CO2 emissions, it's very cheap. And it's fairly reliable as long as you take care of the fuel chemistry to make sure that the fuel doesn't turn into jelly and is ready to go when you need it. So it doesn't trouble me. It's just there as an emergency backup, and that's how I use it, as an emergency backup. And in fact, I don't even, when I need portable power elsewhere on the farm, I don't lug the gas generator around. I have an inverter and a bunch of those lithium-ion batteries, and I lug those around because it's silent. I can run my power tools, my nailer or whatever, charge up my the batteries on my battery electric chainsaw or whatever I need. There locally, and I don't hear the stupid engine running. It's nice and quiet, and I can enjoy the peace and quiet of the woods out on the farm, and not worry about the noise. We only run the gas generator when we really need it. And honestly, I see that as a model for how we'll decarbonize the grid. The last 10%, the kalt Dunkelflaute, as the Germans say, the cold, dark doldrums when the wind doesn't blow.
Yes.
How will we deal with that? We'll burn natural gas 5%, for 2 weeks a year, 5% of the time.
Yeah.
Why would that trouble us? Decarbonization will be a fait accompli at that point. It'll be a done deal. We'll find a way to back deal with, to negate or remove that last 5% if we have to, or maybe we just won't even do it.
It's of so little consequence by then, isn't it? Yeah.
It really is. So, honestly, I see this hydrogen stuff and this focus on hard to decarbonize sectors. I see it as kind of predatory delay, right?
Yes.
So there's an obvious solution. We're going to decarbonize our economy by electrifying everything. That's what we're going to do. Yeah. And if there's something that you don't think we can electrify, chances are the solution is to try harder because you probably aren't thinking
Yes.
creatively enough about it. But what's left when you're done electrifying everything is a handful of things that we need stored fuels for, and we have options. Biofuels are one example that we can use. So I'm not really all that worried about aviation as an example. A lot of people are saying, oh, well, aviation's going to be really hard. Well, the cost of the average plane ticket, some of that is fuel cost, but not all that much. So honestly, I think that we can have aviation switch over to sustainable aviation fuels that are made from biomass, and we can do that in a way that aviation can afford and the flying public can afford. The one that troubles me a little bit is shipping, because the operating cost of ships per ton mile of stuff that they move is about 40 to 60% fuel cost right now, using the cheapest fossils that they're permitted to burn.
That you can possibly
40
get.
to 60%. So imagine you have people saying, oh, well, we're going to use hydrogen for ships, or ammonia for ships, or methanol made from hydrogen and CO2 for ships. That stuff is all going to be a lot more expensive per joule or per whatever unit of energy that the shipping industry would use. And that's going to make a direct impact on the cost of shipping stuff that is not trivial. I mean, multiplying the cost by 2 or 3 times. So honestly, I think the shipping industry is going to be the last vestige of transport to decarbonize.
Right.
It's hard. It's international. It's a cutthroat business. Very, very cost competitive. A high fraction of the cost is energy cost. And internationally very difficult to regulate. So getting an international carbon tax in place in every place in the world, that's a hard thing to imagine, right? So I think honestly, shipping is going to be the last one of transport. Trucks not going hydrogen, definitely going electric.
No.
Cars and light trucks, forget about hydrogen. It's just a dead dog of a technology. Aircraft, like I said, I think the short distance aircraft will do electric, but the longer distance aircraft, you really need a liquid fuel, and so biofuels make the most sense there. And trains and the like, electrification is largely the solution, with or without batteries. And for the really long distance, remote and rural transport, like the trucks that are resupplying First Nations communities in northern Canada, as an example, we're not going to use electric for those, but we're not going to use hydrogen either. Honestly, we're probably just going to keep burning fossils for those applications, but they amount to 3/4 of nothing in terms of greenhouse gas emissions. Just like the diesel generators that people in First Nations communities are running to make electricity for themselves because it's cold and dark up there in the winter. From a fuel logistics perspective, they need a liquid fuel, and they're not going to be running small modular nuclear reactors. I mean, that's madness. No. The notion of those up on First Nations communities just gives me the willies. For the poor people that would have to live around them and contend with their experimental nature. So, I really, honestly, I don't see this focus on the hard to decarbonize sectors as being
it's an interesting point.
It's predatory delay. And that's one of the things that we say, the Hydrogen Science Coalition makes a point of that what we don't want hydrogen to do is to delay existing electrification or energy efficiency means, because that's not in the interest of decarbonization. Clearly, it's better to switch to the thing that we ultimately will be using and leave the molecular middleman out of it if we can.
Paul, what I would love to do is a 3-hour podcast with you, but I've gone over my my standard hour by some time, which is great. And this is definitely not a criticism, but it's been amazing listening to you. Incredible detail and thought that you've put into this topic. Really hope you enjoyed that. Can't wait to tell you about what My Energy are doing. Apart from all the amazing things they do already, they're doing even more amazing things. Can't wait to get more exciting guests on the show. And boy, have we got some lined up. The economics of energy. Oh my God, I'm so excited. Not going to talk about it now. Lots and lots of really good stuff coming. Please do subscribe. Please do tell your friends. Please do spread the word. Please do leave a nice, it's like a review on the podcast app of your choice, or even on on YouTube. Give us a thumbs up. Those things help spread the word. I don't know how, but I don't have to know how because I'm old. Don't need to learn those things. There's more important things for me to do. But that would be a really good thing if you can give us a nice review, give us a 5-star ting, bing, whatever that stuff. That would be wonderful. That's it. As always, if you have been, thank you for listening.